Here's warm-up number 34. First, we're going to simplify this radical, and we've got it has an index of 4. It's a fourth root. So I'm going to be looking for quadruplets. I'm going to start breaking apart the 81x. So 81 is 9 times 9, and then I could break each 9 into 3 times 3. So when you break it apart all the way down, that's what I get. And looking for quadruplets, I found some. There's a set, so one of those will get out, and the others won't. And then the x, since it's not isn't part of a quadruplet set, it's going to stay in the inside, and this is in simple radical form. And I'm finished. Okay. Looks like this is having a little trouble focusing today. I don't know why, but that's how it is. Okay, so next up, I have a radical in the denominator here. You can't just multiply by root 3 over root 3 because you'd have to distribute the root 3 to both the terms here. So you'd have 2 root 3 plus 3, and then you'd still have a radical in the denominator. So what I want to do in a situation like this, when I've got a complex number in the denominator, I want to multiply by the conjugate of the denominator. So the conjugate of 2 plus root 3 would be 2 minus root 3. And since I'm doing that to the denominator, I want to do that to the numerator as well. Okay? And whenever you multiply by the conjugate like this, it should work out so that there's no more radical in the denominator. So on the top, I'm just going to distribute the 6. So that would give me 12 minus 6 root 3. On the bottom, I'm going to think about foiling this. Okay? So I've got a, let's see, when I FOIL this, the firsts will be 4, because it's 2 times 2. Outer will be negative 2 root 3. Inner will be positive 2 root 3. And the last, this is the part where I feel people mess up the most, but it's a positive times a negative, so it's going to be negative. And that's going to be the square root of 9, right? The square root of 9, which is actually going to be 3, right? Because you'd have twin 3's down there, so that's going to simplify to 3. Also, the outer and inner are opposites of each other, so they will just cancel out, okay? So then on top, I'm just leaving this as 12 minus 6 root 3, but on bottom, I've got 4 minus 3, so that's going to simplify to 1 in the denominator. So I've got 12 minus 6 root 3 all over 1. Well, that's just going to be 12 minus 6 root 3. And that is simplified, and that's in simple radical form. Okay? All right, next one. This time I've got a fifth root, so I'm looking for quintuplets. And I've got 15 of these 3's. So you could write out 3 times 3 times 3 15 times if you wanted to. But I'm just thinking, how many sets of quintuplets am I going to have? And so, you know, I'll have, there's a set of quintuplets, there's 5 3's, right? And hey, here's another set, so that would be 3 to the 10th, and then 3 to the 15th is going to look like this, right? So then each one of those represents a set of quintuplets. So a 3 is going to get out here, a 3 is going to get out here, and a 3 will get out here. And there won't be anything left on the inside, so I've got 3 times 3 times 3, and that's going to come out to exactly 27. Okay. All right, next up, I'm going to solve this equation. So first thing I'm going to do is isolate the binomial. So I'm just going to subtract 3 from both sides of the equation. So then I've got x plus the quantity x plus 5 to the third equals negative 8. Okay, and now I want to get rid of the exponent, so I'll take the square root. Not the square root, I'm going to take the cube root because it's raised to the third power, okay, of both sides. So this will give me just x plus 5 on the left. And don't put the plus or minus when I've got an odd root. So this is the cube root of negative 8. And you might think, oh, wait, that's imaginary, but it's not when there's an odd root. Okay, so you can think of this like so. It's negative 1 times 8, and then if I break up the 8, it's 2 times 2 times 2. So I found some triplets there, and I actually have another pair of hidden triplets because if I take negative 1 times negative 1 times negative 1, if you think that through, that's going to equal negative 1. So this is equivalent to that, right? So you can take the cube root of negative 1. The cube root of negative 1 is negative 1. Okay, so now thinking about the triplets, got triplets here, so a -1 gets out and a 2 gets out. So I've got x plus 5 equals -2, and then just subtract 5, and x will equal -7. Okay, and the last one. So I'm going to take the fourth root of both sides of the equation, but before you do that, simplify it as much as you can. So in this case, I'm just going to divide the whole equation by 4, and then I've got 5x plus 7 all raised to the fourth is going to equal 16. Okay, so now I can take the fourth root of both sides. Okay, and when I do that, since it's an even index, I'm taking the fourth root. This would be the same with the square root or a fourth root or a sixth root. Then I have the plus and minus. So I'm going to take the positive and negative root, fourth root of 16. Okay, so let's start breaking up 16. Well, 4 times 4 is 16. So 2 times 2 times 2 times 2 is 16. So the fourth root of 16 is 2. So that's going to simplify like that. Okay, and now I'll start simplifying this. So let's subtract 7 from both sides. I'm going to slip this in front of the plus minus. Okay, and then I'll divide by 5, divide the whole equation by 5. Like so, okay? Now you could write it like this, but that's not a great way to write it because we can simplify this further. So let's think about this. X could equal -7 plus 2 all over 5, or x could equal -7 minus 2 all over 5. And we can simplify both of those, right? This is going to be -5 over 5, which equals -1, so that's a solution. Oops, that's off screen there a little bit. This one is going to be -9 over 5, which we can't really simplify anymore. I guess you could write that as -1 4/5 or -1.8. And there we go. That's the end of the warm-up, and I will see you next time.